Good day everyone. My name is Friso Brouwer and I will be presenting today's webinar organized together with DGB Earth Sciences. A bit about myself. I've been working in the geophysical field for about 20 years. I have worked technical and managerial roles with DGB Earth Sciences and Icon Science. Since 2017, I've been working for myself as independent geophysical consultant. I've maintained a close relationship with DGB Earth Sciences, and their OpendTect software is one of my main software for geophysical work. Among others, for the quality of their base system and the flexibility found in the plugins. Today's webinar will show some of the power of this system. The name of my consultancy is i3Geo, with the 3 I's standing for interpretation, inversion, and integration. Inversion stands for the ability to extract quantitative data from the seismic volumes using techniques such as seismic inversion and machine learning. Interpretation stands for the ability to convert seismic data to geological information. Integration is the ability to merge the results of the previous deal with information from other subsurface disciplines, with the ultimate objective being, for example, pinpointing prospects, create understanding of how to optimize exploitation of a reservoir, or find suitable locations for things like CO2 storage or harvesting geothermal energy. i3Geo's aim is to excel at all these disciplines. Today's presentation will focus on putting together a set of technologies for a quick initial investigation of a possible prospective zone, mainly for the purpose of reservoir quality, but if DHIs are hiding in the data, they could be discovered as well using the same workflow. Any such workflow must meet a couple of conditions. The workflow needs to be quick. The workflow needs to be reliable, that is, given a set of conditions fulfilled, the workflow must yield good results always. The workflow needs to be thorough, so quick should not go at the expense of quality. The plugin tools used in creating this result will meet exactly these conditions. The workflow is quick, the workflow is proper and thorough, using inversion results, better horizon tracking tools, and extracting the full characteristics of the seismic data using a machine learning algorithm. The workflow I will demonstrate has the following steps. First, data quality improvement. Then creating a slicing model to be able to inspect the data along geological slices, sensible slices. Inverting the data to relative impedance and looking at layer properties. Segmenting the relative impedance data in zones of similar characteristics. And finally, inspection and interpretation of the data along geoslices and sections. The dataset I will be demonstrating on is known by us as the Maui dataset, after the Maui field in New Zealand, and is available from the New Zealand Petroleum and Minerals Department on this website. The dataset is located in the Taranaki Basin, which is west of the New Zealand North Island. The interval of interest in our analysis is somewhat above the actual Maui field, which lies in the Sinareft sequence. Our target is somewhat later in time and is a marine channelized sequence. A little fun fact, please note the presence of the Mount Taranaki stratovolcano in the onshore part of the basin, a not very common sight in most petroleum provinces, and a beautiful prominent mountain. So let's have a look at the actual data. The first impression of the dataset is that it, 1, has noise patterns, both random and systematic, and 2, that the frequency spectrum of the data is not ideal and not representative of the geological frequency spectrum. This is shown in one of the later slides. To address the noise patterns, I built a sequence of structurally oriented filters that are especially designed to remove footprinted noise in certain directions. This is followed by a final structurally oriented filter to remove remaining random or spiky noise. Both filters use DGB's dip steering plugin. Comparing the before time slices with the after time slices, one can clearly see the amount of noise reduction and improvement in data quality. These filters are followed by a frequency optimization step using ARK CLS SSB or Seismic Spectral Blueing plugin. The SSB uses the sonic and density logs found in the wells to create the calibration geological reflectivity spectrum. Over the seismic bandwidth, the spectrum of the seismic data is then matched to this geological spectrum, giving a geological optimized view of the data. Here in the original data, we see that there's a wide bandwidth, but that the bell-shaped frequency spectrum is not optimal nor representative of geology. After applying the SSB operator, the spectrum is flattened and the amplitude increases with frequency, which is the bluing effect. In this example, we see how SSB improves resolution, but also provides a more geological view of the data. After bluing, the elements of the fixed channel, A, and B, the levees, are much better expressed. The elements of fin channel C and levees D become only apparent after bluing. Also, the precise stratigraphic relationship of event E in relationship to channel A and the neighboring strata here become clear after bluing, revealing this reflection being possibly the top of a sheet or an overbank splay. These two simple steps significantly improve the data and make it more suitable to follow up workflows such as interpretation of horizons or analysis using machine learning. Further in this workflow, I like to be able to inspect data along geological sensible slices. I use the OpendTect HorizonCube plugin for that in a model-driven mode. Still, I need to interpret framework horizons. The lower horizon, seen in yellow, is simple to interpret, as it's a regular continuous event with constant polarity and amplitude characteristics. The top of the interval of interest, the black horizon, is more difficult to interpret, as there is paleotopography, varying types of layer contrast, and the ideal horizon does not always follow a precise timeline, as the purpose is to build the optimal slicing model. For these kinds of difficult horizons, the Inversion Plus Horizon Tracker is an ideal tool, using a hybrid of amplitude tracking and inversion of the seismic dip to track the best horizon. So I can follow well-defined events, like here, where they are present, and bridge difficult areas, like here, based on the seismic dip. The next slide gives an impression of the slicing model, with proportional interpolated horizons at the sub-resolution interval. Depending on the geology and the seismic data, other methods of creating a slicing model may be used, including data-driven. One of the ultimate objectives in this characterization is to segment the seismic data in zones of similar characteristics. This can be done with the reflection data, but this has the disadvantage that the data represents contrasts, not volume. It is easy to convert zero-phase reflection data to a first-order estimate of relative impedance using ARK CLS SEI or Seismic Coloured Inversion plugin. Again, this is calibrated from the sonic and density logs, and again involves a transformation of the frequency spectrum. In addition, also the phase of the data is shifted. After applying the SEI operator, the data represents a relative impedance and can be directly related to layer properties. Comparison between the reflection data and relative impedance data show that first, reflection doublets, like here, are collapsed in a single layer that is easier to characterize. Second, transparent zones in the reflectivity data, essentially meaning low local reflectivity, are hard to cluster, as it essentially means no change with depth. Transformed to the relative impedance, we see higher or lower value layers that can be characterized by waveforms. There are several ways to inspect data for paleogeomorphological patterns. One approach is to look at the raw data, in this case relative impedance. This will provide a local data point only. To incorporate additional data, such as peak amplitude, frequency, and phase, one can use a set of instantaneous attributes. Or alternatively, like I do, the waveform can be used. The waveform contains all data normally represented in instantaneous attributes, but without any loss of information or artifacts due to transformation. To organize and understand the different waveforms available in the dataset, a clustering neural network technique called UVQ is used. This technique was first developed by Dr. Paul de Groot, who is panelist to this webinar. His original application used waveforms in the 2D sense, tied to interpreted horizons or surfaces. Since a few years, I have extended this original workflow to work volumetric as well. In summary, waveforms are extracted at many example locations in the zone of interest, like shown here. The UVQ neural network in the training phase will create a library of template waveforms that are the most common in the data and may represent discrete underlying geological features. In the application phase, the complete dataset is mapped by assigning at each point the index of the closest waveform match. In the middle display, template waveforms created by training the UVQ network are displayed. Waveforms with the trough around the time in 0 millisecond sample represent soft layers, and vice versa. The waveform templates cover a range of amplitude and frequency characteristics that are representative for different sorts of layering. For example, A, very soft and very low frequency, possibly thick. B, very hard and very low frequency. C, soft and high frequency. D, practically no amplitude. Each template waveform is associated with the interior index. The UVQ application does require some knowledge about how the clustering algorithm works and how to set up hyperparameters such as waveform length and the number of clusters. For new users, training or consultancy to gain experience is recommended. In this dataset, we have used a wider zone of interest for UVQ training, and a total of 44 classes. Again, the waveform templates can be seen here, and they represent a large range of amplitude, frequency, and polarity characteristics. The color bar on top indicates how we represent the index of the match wavelet in the 3D volume. When we look at the data at large, we see how different waveforms are distributed differently throughout the volume. Some waveforms, as those represented by the green color, are present throughout the volume and may represent background shaly deposition. Others, like the blue and the yellow represented waveforms, are less abundant, but form a layer of constant presence and thickness throughout the volume. This indicates these layers were deposited in an even manner. At other locations, like here and here, we see clusters that are more local in nature, and they will represent several discrete depositional elements being present at the same stratigraphic zone. It should be noted that by referring to the polarity of the center lobe of the reference wavelet, it can be inferred whether a layer is relatively soft or hard, with the soft layers having a trough as center lobe and being potentially most interesting for exploration. Homing in on the precise zone of interest. Now the data will be sliced using the model created earlier, starting at the bottom and moving to the top. I will first run through the complete sequence to get an impression, and then highlight a few slices for additional interpretation. What we saw going through the sequence is that there are very distinct changes from bottom to top. At some levels there are more abandoned meanders. At other levels channels are meandering but through going. There are levels where the straight channel plus lobe geometry is dominant. Seeing these changes, I'm going to highlight 3 slices for a more detailed interpretation. Stratigraphic slice 7. At this lower stratigraphic level, many narrower channels that are chaotic and strongly meandering are seen. Features A to the side seem to indicate the outer boundaries of the depositional fairway. Elements like splay B and oxbow C are easily recognized. Channel E terminates in a zone with a dendritic pattern indicated by F. Both features C, channel E, and the pattern here indicated by F have soft signatures and may represent good reservoir quality sand, possibly coarse-grained sand at the bottom of the channel sequence. Stratigraphic slice 4. At the intermediate stratigraphic level, 2 channel systems are observed. A more sinuous system indicated by F, and a more linear system indicated by A, which is our focus. Channel A terminates in lobes B and often exhibits the same class C at the edges, representing finning or levees. This is especially apparent in the UVQ class display. Though covering a large area and being volumetric interesting, channel A, lobes B and oxbow F all have hard signatures, indicating possible lesser quality for a reservoir. Stratigraphic slice 0. At this highest stratigraphic level, the sinuous system A is more dominant. While meandering, the channel is well organized compared to the low stratigraphic levels. It is wider than the same system observed in stratigraphic slice 4, which was the intermediate level. The channel itself is characterized by lack of amplitude, as we can observe from these template wavelets, which are represented by the green color here. This possibly indicates infill with the similar phases as the background shale. Point bars B are very recognizable and have a hard signature. Further, indicated by C, some overbank splays are visible. Finally, we can focus on the question: where are the best quality sands, and would this be a good reservoir interval? The sequence shown in the previous slides represent the waxing and waning of a depositional fairway. Softer layers representing better reservoir quality may occur deeper in this section, possibly being coarser grained lag deposits, sorted and cleaned by early currents eroding the channel. Towards the middle section, layers are harder and represent lower reservoir quality. Towards the top, wide sections with low amplitude are observed, likely to represent infill or draping of materials very similar to the embedding shale formations. Good reservoir quality sands may not be widespread in this zone. This conclusion is consistent with the observation that most of the depositional features seen are erosional in nature, placing them more up dip in the depositional fairway. Deposits here are often characterized by poor sorting due to shorter distance to source and by later infill of low energy fine-grained deposits after initial erosion by high energy passing currents. Still, this is a satisfactory result. Did we spend too much time to do this analysis? No, we did not. Did we use appropriate high-end technologies that are also quick to be confident that the result is reliable and that additional analysis would not provide significant other results? Yes, we did. So we're happy to pass this on without having spent too much time and without feeling that we possibly overlooked something. In conclusion, I've shown how to use several plugins to OpendTect, created by DGB Earth Sciences and ARK CLS, into a workflow to do a quick, detailed, high-resolution inspection of a possible prospective zone for reservoir quality. The workflow applied is quick, simple, reliable, and thorough. For more information about the workflow, the software, or possibilities for training or consultancy to apply this workflow yourself, please contact myself or my colleagues at DGB Earth Sciences at the displayed email addresses. This concludes the presentation. We now have time for questions for my colleagues, panelists, and myself. Thank you for watching.